Okay, so I think we can start. So, okay, so that is mosquito. I was thinking, my pen is not here. How is the cursor going there? Okay. So, we were talking about generative models because the course is about generative models. And we have till now talked about 4 families of generative models, more or less. Just to quickly recap, what is a generative model? It's a class of machine learning model that attempts to learn the distribution of the data so as to enable generating new data or new samples from the distribution. So that is the definition that we have been following. That is anyways the definition. And we have talked about 4 families, 4 types of generative model. What is the first generative model we talked about? Autoregressive generative model, right? So I will write it down because there was a break, so some of you might not remember. So we'll do a quick recap of things we have done and then we'll move ahead. Okay. So generative model attempts to learn P of D, I mean the data likelihood, not likelihood, the evidence basically, right? The evidence is what it tries to learn, and it tries to learn that so that the purpose is so that it can generate new data. And then if I talk about application, one application can be anomaly detection, and obviously generation anyways is objective of its own, right? Now, as I was saying that we have talked about 4 types of generative models till now. The first one was autoregressive generative model, as correctly pointed out. The first one that we discussed was autoregressive generative model. How does it work? Remind me. What do we do in autoregressive? Product of conditionals, autoregressive manner, right? So what we do here is, if I have to find out P of x, let's say I will do product of conditionals xi given x less than I equal to, let's say, 1 to k, where k is my number of pixels, number of timestamps, number of points in a single data, right? So this is basically, if somewhere we are using this, we can call it a autoregressive generative model, right? We talked about at least 2 types of autoregressive generative model. You have, including the homework or practical, you have done 3 types. The examples were, the first one was fully visible sigmoid belief network. So examples include, because it is a family, so it is not a single model. So examples include fully visible sigmoid belief network. Then we did NED. Then there is MED, and there are others also, by the way, but I mean, these 3 at least you are aware of. So this is kind of the fundamental, and on top of that you can always build. But these 3 at least I think you have either coded it already. I don't remember it was for practical or homework, but either you have already written the code or you are going to write the code for all of these 3, right? The second one we talked about was latent variable model. So the second one is latent variable model. And in this case, the idea is that there is a latent factor that is influencing the generation of data. And so what you do is you introduce a latent variable. It comes from some P of z and then you have x given z. Generally Gaussian, need not be Gaussian, but Gaussian is a popular choice. X given mu theta and sigma theta. This is any latent variable model, right? What are the different latent variable models we have talked about? At least two. Mixture distribution. The other one is VAE. Okay. There are others also. Gaussian process LVM is also there. In fact, some will argue, I will argue that the next family is also a latent variable model. So there are more as well, but at least these two we have talked about while discussing latent variable model, right? So example, mixture density, mixture density, and then VAE obviously is the most popular one. Then what is the third one we discussed? We have discussed in this course? Flow-based model. Based model. Now for flow-based model, I will not be able to write a different equation like this because it's also a latent variable model. The only idea is that we use transformation of distribution, and to use transformation of distribution we use invertible layers, right, which can give us z to x and x to z both. That is the idea of the flow based, right. So here there are two key ideas. One is transformation of distribution. This is one idea. And then the other idea is invertibility or invertible layer. Okay. Now, what are the examples? What are the things in flow-based model we talked about? We've talked about nice. Nice is basically where the volume is preserved, which is not good actually. Then we've talked about real NVP, where the affine coupling layer comes into picture and the volume is not preserved. We've talked about MAF, masked auto encoding flow, and we have talked about IAF, right? The invert one, and we have talked about one or two more actually, right? So here I think we have talked about 4 or 5 examples at least we have talked about here, right? So let me write it down. Here we talked about nice, which is the first thing we discussed where the volume is preserved. We have talked about real NVP. This is the affine coupling one, the most popular one. We have talked about MAF. We have talked about IAF. We have in fact also talked about slightly about planar flow, although it has some challenges of its own. Radial flow we did not talk about, I just mentioned on the fly. And then there was a combination of MAF plus IAF that we talked about, where we do one, the student teacher kind of model, right? So, and there are others also, again, there is GLOW and there are others, but the principle remains the same and we have talked about it. And the last one that we talked about, and that was the last lecture before your minors, is the GAN. What is the idea here? The main idea is here is that you don't use likelihood, you use a network discriminator to train your generative model. So the main idea is discriminator to train your generative model. Discriminator, which is a network to train generative model. Here we actually did not talk about much variations, but there are, but those variations comes in the change of loss function and all of those things, right? You will find some of those in the homework that has been uploaded. So there is some variants of that, but the main principle again remains the same, and that we have discussed. Okay, train generative model. So these are the 4 families we have discussed till now. Today we are going to start discussing about a new family of generative model, which is known as energy based models. We are going to talk about or start talking about, it will take some time. So obviously we will not complete it by today. We will probably not even discuss much about energy based model today. We will just set up the foundational blocks and all of those things. So we will start a 5th family of generative model, which is the energy based model. Okay, and this energy based model you will see later, not too much late, but later will have a very close relation to diffusion model, which is the state of the art right now. Okay, I mean flow matching diffusion. So we'll start talking about energy based model. We'll spend some time on energy based models. It has some challenges, so we have to talk about certain techniques and all of those things. And from there we'll go to score based model and diffusion model, and then flow matching. Okay, so that is kind of, so we are now we are now kind of starting with diffusion model without calling it diffusion model, because this will form the foundation of diffusion model, and we'll see how energy based model transition to denoising diffusion, DDPM, DDIM, and all of those things later in this course. Okay, so today we are going to start talking about energy based models. Although I'm writing energy based model, it is energy based generative model. Okay, why is it called energy based, and all of those things will come later. Okay, again, the objective of generative model is to learn the distribution of the data, and one of the foundational block that we have been using and we have to use in the process of learning the distribution is the PDF itself. We use different types of PDFs, we use decomposition of PDFs. So PDF is something that we use. I mean, PDF is what we want to learn, but simpler PDF is what we use to actually express that complex, intractable distribution, right? So one of the key ingredients of this course, forget about generative model, is probability density function, and that's what we started our first lecture with. The first lecture ended with PDFs, I mean, kind of, right? So for any generative model, one of the key, or maybe the most important, right, key ingredient is PDF. Okay, so remind me, what is a PDF? What is a probability density function? What is a PDF? The definition. It's a function non-negative, so that is one of the property, and integration, not sum. So normalization. So it's a function that satisfies 2 properties, right? And we all know that. One is the non-negativity. It is always greater than equal to 0. It cannot be negative. And the second thing is that if you integrate over all possible values of x, which is generally in many cases minus infinite to infinite, then what you should get is 1, which means it's normalized. Now this is important, so I will rewrite it down again, because this is important in the context of what we are going to discuss in energy based model. So it's a function, and I will put function inside inverted comma f x x such that if xx is greater than equal to 0 and integration fxx dx is equal to 1. This means non-negativity and this is normalization, right? Okay, then this is something you know. So now let me ask a question. Neural network, machine learning in most cases is a function, right? Neural network is a composition of functions, so it's a function. So it automatically satisfies the word or term that is inside the inverted comma. It's a function. So can a neural network be used to represent a PDF? Because it's a function. The common sense answer is yes. It's obviously yes. But then the neural network output should satisfy two properties. And those properties are the neural network output cannot be negative. And if you integrate the neural network for all possible values of the inputs, then it should give you 1. So if these two properties are satisfied by our neural network, then that neural network is a PDF, right? So neural network, although I'm writing neural network, but you can imagine that it need not be neural network. It can be any function, right? Neural network is a function. So neural network is a function, or it approximates a function. I mean, I think that is probably the correct terminology, but that's okay. So if it satisfies non-negativity and normalization, then it can be used to represent any generic PDF, any generic PDF. Why any generic PDF? Because with change of theta, the function will keep on changing. So what we are looking at is for any theta, right? Then only it is not for a given theta, it is for any theta and any x. The output should always be non-negative. And for any theta and for us all possible values of x, if I integrate over x, I should always get 1, which is basically volume preserving, right? I mean, the volume should not change. The probability mass that you get from by integrating the density should not change, right? That is what is needed. And if that is possible somehow, I don't know if that is possible or not, but if that is possible somehow, then that will probably be the most powerful PDF that is there, because that will have the capacity to represent any PDF, because neural network is a universal approximator. So if you can do that, that will be the best case scenario, right? This is the motivation of energy based model. That in energy based model, you want to use the neural network to directly represent the PDF, not some mapping from samples generated to the new samples, as we did in GAN, as we did in VAE, as we did in flow based model, normalizing flow. But rather, the neural network that itself represents the PDF. Unfortunately, this is very difficult. And we will see why is it difficult. Because it's obviously a function, so why is it difficult, right? So, first condition is non-negativity, which means the value that it gives should always be positive or 0. This is kind of easy to satisfy. You can just square the neural network, whatever the output is. That's a always non-negative quantity. You can take an exponential of that. That's always a non-negative. And you can come up with 10, 20, 30, 100 different ways of ensuring that it is non-negative for any x and any theta. So satisfying non-negativity is trivial, right? Satisfying non-negativity is trivial. Examples, as I said, let's say p theta of x can be f theta of x square of that, where f theta is my neural network, p theta is basically representing the PDF. I mean, I want it to be PDF. It is not yet PDF because obviously I also need to satisfy one more criteria, but that's what my target is. Let's put it that way, right? So that's why I'm using the term p theta, but it's not yet PDF. Keep that in mind. Or you can say that, okay, I don't like square, I'll do exponential. And that's also a possibility. And you can come up with in other ways, right? As I said, you can come up with, you say not square, 4, 6, 8, keep on doing that even, right? And you can always get it. You will say, no, I will take a, I mean, you can do n number of things and you can come up with this non-negativity. So that's trivial. But what about the other criteria? To ensure that it is always normalized, which means that for all the x that you can give as input to the neural network, if you integrate over that, it should give you 1. This is non-trivial. In fact, this is non-trivial to the extent that you cannot guarantee it for a generic neural network. You can always come up with specialized neural network that will probably hold this property, but then that means you are compromising on the expressiveness. You're compromising on what functions it can represent. So that is not something we want. We want a generic neural network to be normalized, but that is not possible. Okay, we will not be able to do that. Even we don't even care if it is not normalized. Even if we can find out the normalizing constant, that's also fine. We'll just divide with it and I will get my PDF. But even finding the non-normalizing constant itself is extremely difficult for a generic non-linear function like neural network. Okay. So satisfying normalization is non-trivial and almost impossible, right? I mean, no, because what we are talking about is not approximation. We are talking about exact. We are not looking at something that will be approximately non-negative. We are talking about from a theoretical point of view, is it possible? Not in an approximate sense. Okay. So satisfying, and even in that there is a problem, by the way. Regularization. Regularization will do only over a training data. During test time, how do you ensure that it will hold the normalizing property? It will be difficult actually. It will be much more. That is one of the problem of energy-based model, that it's very difficult to sample from it. So it is giving you some arbitrary PDF. How it will give, we have not yet reached there, but assume some arbitrary PDF. Will not be able to sample from it easily. We have to use something like Metropolis testing, Hamiltonian, Monte Carlo, and all of those things. So that's why I was saying that in the beginning I said there are tools also that will come into play. I have to discuss. So this will take us to Metropolis testing and all of those things. Maybe next lecture it will take us there, and we'll discuss that the 2 lectures after that maybe. Okay, so it's very difficult to sample. If you like, knowing PDF does not ensure that you will be able to sample, but it helps you evaluating the likelihood and all of those things. Okay, so yeah, but we'll come there later. Okay, so satisfying non-normalization is non-trivial, almost impossible. The reason is that uh, you will not be able to integrate it. It's a high dimensional integration, right? So you will not be able to do that. And we'll talk about that later when we talk about the cons. Along with that, this is another limitation. So these two are the main limitations. You don't know how to compute the normalizing constant, and you cannot sample easily. Sampling is hard. Okay. But satisfying normalization is non-trivial. So what is the solution of that? One easy solution is you can select simpler functions where you can compute the integration analytically. That is one obvious solution. And I will show you now that we have actually already done that. We have already done that in one of the models, one of the 4 models that we discussed. Okay. So one option is one option is to select models, mathematical models, simpler models, where one can integrate and compute the normalization constant, because that's what we want. I mean, we are okay with having a non-normalized, unnormalized thing that will give us our unnormalized distribution. But if we can integrate it, we will divide it by that, we'll get a normalized version. What are some of the examples of this? I mean, you already know this. So for example, if I use a function something like this, right? Exponential of minus 1 by 2 sigma square x minus mu square dx. If I have a function like this, we know what is the normalizing constant. What is it? Square root of 2 pi sigma square, or sigma root 2 pi, right? We know that. If we have, let's say, exponential of minus lambda x dx, this goes from 0 to infinite actually, then what do we get? Anyone knows? 1 by lambda. This is the exponential distribution, right? The PDF of exponential is lambda exponential of minus lambda x, and it is non-negative, so x goes from 0 to infinite. Okay. And similarly, you can think of others also. You can think of Poisson, you can think of Bernoulli, you can think of binomial, you can think of gamma, beta, and all of those things. So basically, the functions for which we can do this analytically are actually the known PDFs. They are the known PDFs, and that's why they are known, because you can do it analytically. The moment you could not do it analytically, they will be unknown. All the known PDFs that we can imagine are the ones where you can actually find the normalizing constants, right? But you will see that I gave you two examples. So there is one more thing I would like to discuss here, which I did not discuss as far as I remember. So I talked about two distribution here. The both of these are having exponential in common. So there is this family of distribution which is very popular and used widely in machine learning and statistics is known as exponential family. So exponential family is a family of distribution which encompasses many of such distributions for which uh, not all but many for which you can actually compute it analytically. Okay. So in general, we have exponential family of distribution, and how does it look? So fx x, and let's say it is parameterized by theta. So then this is the exponential family takes the following form: cx, sorry, cx nu, sorry, eta theta exponential of tx dot r theta or rx dot t theta. Doesn't matter, right? So this is one form, one of the popular forms of the exponential family of distribution. There are other alternative forms also. There are some forms where they don't write r theta, they write only theta. So r theta is theta, you can always write. There is no issue with that. Okay. But this is one of the popular forms, I will say, of exponential family of distribution. Why is it important? It is important because many of the known distributions falls under this family. So what are these known distribution? I'll give you some examples. Gaussian is, is in the exponential family. Exponential is in the exponential family. Poisson's is in the exponential family. So now you are wondering everything that is having exponential is in the exponential family. That is not true. Bernoulli is in the exponential family. Gamma is in the exponential family. And there are Huissert is in the exponential family. And there are many more. I don't remember all of those. Student's T is not in the exponential family. That is one example that is not in the exponential family. Okay. So you can understand that by operating on this, if you can come up with something useful on this, that will hold for Gaussian, that will hold for exponential, that will hold for Poisson, that will hold for Bernoulli, binomial, Huissert, gamma, and many more. So that is why it is important. It is always important to generalize things, because if you can define and derive certain things on the generalized one, everything that falls in that family automatically should satisfy those properties. And that is why this is very popular. There is one more reason it is very popular, but that we are not covering this time around, is that this is a very popular, most of the distributions that are in the exponential family have a conjugate, something known as conjugate prior. But I leave it there itself. If you're interested about conjugate prior, you can search it online. You will find a very nice Wikipedia page. If you want to know more, last time I covered it, you can go and check it out. But when you do Bayesian, there is a concept of prior, and conjugate prior helps you do things analytically. And most of the likelihoods that belongs to exponential family have a conjugate prior. Okay, I think all, if not most. It might be all actually. Okay. Anyways, so theta are the parameters. Okay. So I'll give you one example. I'll show you, but before that, let me write something. So see, in this there is one interesting factor. This Tx, right? This is known as sufficient statistics, which means if you know these things, you do not need any x. This Tx, and obviously there is Cx also, but for now let us only consider Tx. So Tx is enough for you to completely write down this expression. So I'll give you one example of the sufficient statistics that we encounter in many cases, like for Gaussian uh, distribution. I think mean and standard deviation under sufficient statistics. That means if you know those, you can write down your PDF without knowing anything. Okay, I'll write it down. Okay, I'll write it down. Wait. Okay, so you are right. You're right. But yes, uh, you are right. Actually, I messed up. Wait, let me change it. Actually, you are right. It should actually be P theta and Rx. Okay, and P theta is the surface instance. You are right. Okay. Anyways, okay, going ahead. So I said examples includes examples of distribution belonging to examples of distribution belonging to exponential family. If you have to write down, then they are Gaussian, Bernoulli, gamma, Wishart, and there are many more. Okay. So let us take the Gaussian one and let us try to see that how we can rearrange the Gaussian PDF such that it falls in this exponential family. Okay. So for Gaussian, we know that it looks like 1 by sigma root 2 pi exponential of 1 by 2 sigma square x minus mu square. Okay. This is, if I open the bracket inside the bracket, so exponential of minus x square by 2 sigma square minus mu square by 2 sigma square plus x mu by sigma square, right? So you can see that there is this mu square by 2 sigma square that is independent of x. So that term we can take outside. Okay. Not because it is independent of x, we can take it outside, but we will take it outside. So this is equal to then 1 by sigma root 2 pi exponential of minus mu square by 2 sigma square multiplied by 1 multiplied by exponential. Now what remains inside the exponential? Minus x square by 2 sigma square plus x mu by sigma square. So now remember we have to write it in form T theta dot Rx. That's the dot product. So what is T theta in this case? T theta in this case is um, the first one is minus 1 by 2 sigma square, and the second one is mu by sigma square. So this becomes my T theta, and then Rx, which will be so this I have written in transpose form. You can see because dot product A dot B is equal to A transpose B. So I have taken the transpose of that, and the other term is minus x square. Okay, x square. I have taken minus there, right? X square and x. So you can now see that this term here is your, what was it? Eta theta. Eta, this is your eta theta. This is your Cx, which is constant in this case. This is your what? T theta. And this is your Rx. Basically rearranging, right? Nothing else. You can try with the others. I'm not doing those, but you can write, if you can write some distribution into this form, that's in the exponential family. As simple as that. If you can rearrange and write a distribution into this form, that's in the exponential family. Okay, and it is very popular because there are certain things you can prove about exponential family, and many of the known distributions falls under this family. Okay, so that is the reason it is very popular. Okay, any doubt till now? There is no generative model till now. Statistics, right? So this is clear. Okay, so this is clear. So now let us move ahead in that case. Energy based model. Now let us go there. So what we have discussed till now? Yeah, any, and it will change based on the family, the distribution. For Gaussian, C will have a different form. For exponential, it will have a different form. That can be vectorial function. Yes, because it will have. I mean, I have shown only univariate, right? You can imagine the exponential family for multivariate. In that case, it will have to be. No, you were talking about the outer one or the inner one. The outer one has to be scalars. The inside one will be vectors, because the ultimately PDF always is a scalar. In the sense, hmm. Parameters are there, right? Theta are the parameter. Theta are the parameters, and you will see that whatever is the parameter of the original distribution, will theta will actually t will actually function of those things only. Like think r, r is r of x, right? So r of x. So think about like this, right? I think this is a very easy way of thinking about it. Think about Gaussian. What are the characteristic of Gaussian? There are two primary characteristics I can think of. One, it is squared exponential, right? So that means r of x should have a square and a linear term at least. R of x cannot have a cubic term. So you can see the relation, but if there is an exponential of a cubic, if there is some PDF hypothetically, then you know that R of x would have cubic, square and linear. So that kind of one-on-one correspondence is there. The second thing, what do we know about Gaussian? That theta for Gaussian is mu and sigma. So that means this T of theta and theta, whatever it is, will be some function of mu and sigma. It cannot be some function of kurtosis or skewness, because if Gaussian, it is we know that the first two moments are enough to define a Gaussian. That means when we represent Gaussian in the exponential family, the first two moments should be enough for representing this T of theta as well. But if there is some distribution, again hypothetically, where the parameters are, let's say it's a 3-parameter distribution, Weibull 3-parameter distribution. Weibull is not even here, but anyways, let's assume there is some distribution in exponential which needs skewness also. Then T of theta should also be a function of skewness. So that is how it is related. But that also means that T of theta will keep on changing from problem to problem. R of x will keep on changing from problem to problem. P of x and eta of theta will also keep on changing from problem to problem. But ultimately, you should be able to come to this form: Cx eta theta exponential T theta dot Rx. That's the idea. Okay. And in many books, you will find that they don't write T theta, they write theta. And you can imagine that T theta I am writing because I am relating this theta with the mu and sigmas. You can directly write theta, it will still be function of mu and sigma, but then you will don't call it T theta, right? In that case, this T theta, you can write theta. I mean, it's your naming, right? How does it matter? Okay. 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 So what we have discussed till now, see, we told that PDF is a function that satisfies two properties. One of that I can easily satisfy, the other one I cannot. I also said that if we can represent a PDF as a function of, I mean, as a neural network, that will probably highly expressive, right? But that is generally not possible. The reason being, normalizing constant is not known, it's intractable, it's non-trivial, whatever you want like to call it. More or less, these are the three aspects that we have discussed over the last 40 minutes. Only these three aspects is what we have discussed. So in energy based model, then what we can do or what is done is as follows. In energy based model, you write the distribution, and it is now a distribution. So P theta of x. Remember when I wrote P theta earlier, it was not yet a distribution. I wanted it to be a distribution. Now it is a distribution. Okay. P theta of x is equal to 1 by z theta exponential of f theta x. What have I done here? F theta of x, what is it? It's a neural network, any arbitrary neural network. What is exponential doing? Making it non-negative. Z theta, I do not know. So let's assume this z theta. It's unknown, but let's assume it's unknown and it's z theta. And I write it like this. So if I write it like this, is it not a PDF now? It's a valid PDF as long as z theta is equal to integration of exponential of f theta x dx. It's a valid PDF, right? Exponential ensures it is non-negative, and the definition of z itself ensures that it is normalized. Yes, you can argue that, but how will I find it? It's intractable. Yes, we'll see that maybe in the next lecture. Okay, maybe not. We'll not see it today, but we'll see that how to handle this z. But yes, z is intractable right now. We will have to do some approximations that we will see later. Okay. So let me write it down, whatever I said. So first thing I said was exponential. One thing I forgot. I'll come back later. Let me discuss this and I'll come back. I told, but I did not wrote it, is that we have already used some generative models where we use the simpler distribution, but I did not give that example. So I'll come back to that. Okay. I just remembered. So exponential is used to ensure non-negativity. Okay. Now at this stage, you might ask, and you should ask, why exponential? Why not f theta square? Why not f theta to the power 4? What is so special about exponential? Can you tell me what is so special about exponential? Hmm? But do you need derivative here? Hmm? Exactly. The first reason is that we generally work with log probability. If you take log of exponential, you will work with actual neural network. So you will have less headache. Because neural network, we know everything is known to us. How to take derivative and all of those things if needed while training. But in general, so we generally work with log probability. So here, if you work with log probability, you will work with the neural network only. That is one reason. There is one more reason. Can you think? Exponential family. Because many of the distributions falls into the exponential family. This also ensures that this is in the exponential family. Because it is exponential of something. If exponential something, you can always write it in the exponential family. I mean, it is always already in the exponential family. You can see, right? Because f theta of x, f theta of x is, you can always write theta times x. Because with some non-linearity obviously, but you can write it. And 1 by z theta is more or less that's theta, and c of x is 1, or it can something can come from inside also. But you should be able to write it in that form. We will not be using any properties of exponential family, but this has that flavor. There is a third reason also, and there is a fourth reason also. The fourth reason I will not tell now. Fourth reason I will tell while telling you why these models are called energy-based models. So that you will wait for some time. The third reason is that exponential also helps you magnify things. So if there is something is very small, it will kind of magnify and it will separate out those things. Square might not do it efficiently. So that is also another reason that exponential is used. The fourth reason I'll talk about later. Okay. So exponential is used to ensure non-negativity. It also helps as we work with log probability in practice. In practice. Yes, you can say that. Okay. And it also is in the exponential family, so there is motivation from there as well. Z theta is basically the Z theta has a name. Z theta is defined as obviously integration of exponential of dx, right? This is how you define Z theta. Is there is another name of Z theta which apart from normalizing constant, it is known as partition factor. It is known as partition factor also. It is the normalizing constant. That's another name. So it's basically synonyms. If you see partition factor somewhere, you should know that's normalizing constant. Okay. But remember, it is constant for a given x, or sorry, it is constant for a given theta. If theta changes, it will keep on. It will change. Okay. It is not a function of x, but it is a function of theta, and that is going to be painful for us because theta is what we want to train for, which means we will not be able to ignore this z of theta during training whenever we reach that point, not today. Okay. So it is going to be little bit painful to handle this z of theta because you will not be able to ignore this while training the model because theta you will try to maximize or minimize. I mean, likelihood you will try to maximize, and that will have z of theta, and so you have to work with z of theta, which means z of theta you cannot ignore. It has to be computed. And computing is intractable, as you can see here. I mean, it's a high dimensional integral. Okay, so you cannot ignore it. So Z theta is the partition factor. Okay. And this you cannot ignore, you have to compute it. So this is basically the basic model, basic equation of energy based model. This is the basic equation of energy based model. Energy based model, you try to write things in this manner. Now, why do we call it energy based model? Any idea? Why do we call it energy based model? Because of this form that you are seeing. If you read statistical mechanics or thermodynamics, this kind of distributions are very common there. It has a name known as Boltzmann distribution that you encounter in thermodynamics and statistical mechanics in general. And because thermodynamics, there it is actually, and there inside term what is there is minus of energy, negative of energy. So the actual form is proportional to exponential of minus epsilon I, where epsilon I is the energy of the ith particle. Because there are particles like molecules moving around in Brownian motion. So that's what it is. So because this form is inspired from there, and because there was energy there, that's why you call it energy based model. The name energy based model has inspiration in statistical mechanics in thermodynamics, and from there it comes into picture. So exponential of f theta x, this type of distribution is commonly encountered in statistical mechanics and thermodynamics. Okay. It is known as Boltzmann distribution. So here the name is Boltzmann distribution, and Boltzmann is a very popular name actually. There are numerical methods known as lattice Boltzmann machine, which is used for solving PDEs in fluid mechanics. Also, you will see that in energy based model, there is a model we will talk about in the next lecture known as restricted Boltzmann machine. So that was lattice Boltzmann method. This is a machine, restricted Boltzmann machine, which is probably the first generative model that is there. And deep Boltzmann machine is the first deep generative model that was developed in 2009 by Hinton and his group, Jeffrey Hinton, right? So, so Boltzmann is quite popular, I'll say. I mean, that has a lot of application, this Boltzmann. So this is so there is a Boltzmann distribution which is proportional to exponential of minus epsilon I by, there is some constant and then t. There are one or two constants there in the denominator. So I'm not, because I'm writing proportional, I can ignore those, and t. And the idea is very simple, that if t increases, then this will kind of, T is basically the external temperature that you give, right? But we don't care about T, so I will just remove T. I just wrote it because I wanted to show it to you. We don't need T. For our case, this is enough. Okay. Where epsilon I is the energy of the ith particle, there is a negative sign here. And that negative sign has a significance. So generally, in a distribution, you try to maximize the likelihood. So as you maximize the likelihood, you kind of reach a point which is the optimal one, right? Whereas for equilibrium, in mechanics, we try to reach the minimum energy state. So maximizing the PDF should mean minimizing the energy. That's why when you see f of theta there, negative of that PDF is the energy in that sense. Okay, so that's an analogy I am drawing. That's not I am drawing, that's an analogy that exists. So if you think it from energy point of view, we'll try to minimize it. Whereas when you look at PDF point of view, you try to maximize it. And therefore, in fact, this is not the only place where you see energy. There is also something known as maximum entropy principle. So there also entropy, that term comes from this energy only. And there but there entropy means the chaos or the uncertainty in the system. And you try to find a distribution that best explains all the uncertainty in the system. So you try to maximize it. So that's the maximum entropy principle. Not used that much nowadays. Its best use is to find out some good prior. I mean, that's all nowadays. Okay, but it was very useful at one stage. Okay, that's the maximum entropy principle. So that is also there. This is the Boltzmann distribution, and the idea is that maximizing the PDF should be equivalent to minimizing the energy. So the way I see it is that if you have a PDF, right, maximizing the PDF means what? Finding out the mode, right? You reverse it. If you reverse the PDF, it will be like finding out the minimum energy basin, which is actually, if you reverse it again, go back to the original one, it is like the mode. Okay. So that's why this negative sign is there. So minus of f theta x, you can think of it as energy. So there is an energy that is there. There is the Boltzmann distribution, and therefore you call it the energy-based model. Clear? Why is it called energy-based model? Which? How does a Gaussian look? Think of Gaussian PDF. How does it look? Gumbel sir? Just reverse it like this. How will it look? This is the minimum energy basin. That is a negative, right? So finding the mode of the distribution is equivalent to finding the area which is having the minimum energy. That's what it is, right? Summation of what? How many samples? Because how will you think? But then during, again, the same thing I told you earlier, during inference, for those samples will it hold? Because this is a constant we are talking about. You cannot, you have to take everything possible, and that will create. Obviously, we'll do some Monte Carlo approximation at some stage, that we have no other choice. But theoretically, you can imagine, right, that it will give you some constant, and that constant you just put 10 more data, that changes. So that is why it is difficult, right, to find. And again, it is intractable analytically in most cases. When I say intractable, because it's a constant. So that's the problem. Okay, but we will ultimately do it some Monte Carlo only at some stage. Okay. So this is the Boltzmann distribution. That's why we call it energy-based model, because it has some correspondence with the Boltzmann energy or energy in general. Okay. Okay. So now let us go back. I missed that part. Let us discuss that, which is that we have seen models, generative models, where simpler distributions were used to model a complex distribution. What is that model? Not exactly latent variable model. I will say that's also a latent variable model. No, there is no Z here. In this whole business, you will find any Z here. There can be Z, but till now, have you found any Z? No. So it has to be autoregressive model. Autoregressive model is the only model that does not have latent variable model, latent variable till now. Because when I'm writing this till now, this is not dependent on having a latent variable. You can have latent variable, and restricted Boltzmann machine has latent variable, But not all energy based model need to have latent variable, which means when you do one-on-one correspondence, you should look at something that does not have latent variable. Okay. There is no latent variable. Is there a latent variable in here? It is f theta of x. Where is the latent variable? There is none, at least till now. Rest. So when I said it, there is none. I mean, when I say, remember what the question is what? What is the generative model we have talked about where we are using this simpler distribution to find the final distribution by composing the simpler distribution? That's not what latent variable model do. That's what autoregressive model does, right? So this would have been earlier, but let's revisit autoregressive model. So in autoregressive model, but it is true there are some latent variable model which you, so latent variable model can also be thought of as a energy based model under some considerations. Okay, that's a different thing. In fact, it's a very big family. Many models can come under, like just like latent variable model. It's a big family. Flow based model is also a latent variable model. GAN is a latent variable model. So just like that. So that is correct, by the way. But when I'm saying we are using simpler distribution composition of that, that's autoregressive. Okay. Autoregressive generative model. What were we doing here? If you remember, we were doing something like this, right? P of x1, P of x2 given x1, P of x3 given x2 comma x1. Right? Now, remember that P of x1 was what? Bernoulli Gaussian, something simpler. P of x2 given x1 was what? Some simple distribution. P of x3 given x2 comma x, again simpler. But that's not the point. The other point is that they were simpler but also normalized distributions. P of x1 was a normalized Gaussian, a normalized Bernoulli. P of x2 given x1 was a normalized Bernoulli, normalized Gaussian, and so on and so forth. And you can show trivially that if you represent a joint distribution as product of normalized conditionals, then the joint distribution is automatically normalized. I'll repeat. If you represent a joint distribution as product of conditionals and prior, whatever it is, where each of those product term is individually normalized, then the joint distribution is also normalized. And this is the most trivial thing that can exist, because simple. This is very trivial because what I've assumed is, I mean, it's not an assumption, it's a fact, but all of these three red are normalized, right? All of these three are normalized, correct? So now let us try to integrate it. Let's see. I want to integrate, so I should integrate over x1, x2, x3, px dx. That's what I have. This is equal to what? Integration of px1 dx1 integration of px2 given x1 dx2 integration of px3 given x1 comma x2 dx3 because remember that P of x2 given x1, when you are integrating it, you should integrate with respect to x2, that's the variable. What is in conditional is kind of known, given. So it should not be x2 and x1, it should only be over. Now each of this is normalized, so each of this integration will give you 1, 1, 1. Product of 1 and 1 and 1 is 1. So it's trivial. If each of these three are normalized, simply the left hand side is also normalized. So this is the property that we have used earlier, but now but this property restricts us in the sense that we have to select these conditionals on the prior in such a manner so that they are simple and normalized. If they are not normalized, the left hand side will not be normalized and we will be stuck in the same place. So that is a restricting factor, right? That compromises the quality of the gen samples you will get, right? So actually, this is one of the limitations that energy based model is kind of addressing, because now you do not need it to be normalized. It can be unnormalized. We'll find out the normalizing constant. How I've not talked about it. So let's say we don't know. So this restriction is kind of uplifted in energy based model. I'll repeat. In autoregressive model, one of the limitations was that each of the conditionals needs to be very simple. Simple in the sense they needs to be normalized. That's why we're using either mixture of Gaussian, which is normalized, or Gaussian, or Bernoulli. Yes, the Gaussian was function of a neural network as mean and covariance, but it was Gaussian at the end of the day. You cannot use some arbitrary distribution there, because then the left hand side will not be normalized. And then you cannot do it in an ancestral manner of sampling, right? So, but with energy based model, that limitation is not there. That is one of the biggest advantage of energy based model. Clear? So this was supposed to be discussed earlier. So coming back, what are the advantages and disadvantages, pros and cons of energy based model? So I was right, I will not be able to go to any of the details. Pros. So what is the advantage? There has to be some advantage, otherwise no one will use it. It is highly expressive. There is no restriction on f of theta. So it's highly expressive. But the list of cons is a little bit longer. What are the cons? I already talked about two. The first one is it is hard to sample, because you are getting some arbitrary distribution. So how do you sample from it? You will need some sampling scheme. Be it Metropolis testing, be it Hamiltonian Monte Carlo, be it Gibbs sampling. Gibbs is generally not used here, but something you need. Okay. So cons are, the first one is hard to what else? Yes. Yes. That is a limitation, right? I mean, obviously. So the second thing is hard to sample, but the good thing is that many distribution actually belongs to that. So that's the reason interesting. The second thing is training is time consuming, because you don't need Z, and Z is interactable. You have to do some tricks there. So training is expensive, sampling is expensive. Till now, all the models we have discussed were either facing difficulty during training or facing difficulty during sampling. This is the first model which is difficult during training and during sampling. So the pros has to be really strong, otherwise no one will use it, right? Slow to train. Okay. Ultimately, all of this, the second one specifically basically comes from or something known as curse of dimensionality. So basically the second limitation actually stems from this. And this curse of dimensionality is there because z of theta is an integration, and if x increases, the number of integral increases. So with one variable, it's a one dimensional integral. With 1000 cross 1000 pixel size, it's a 1000 cross 1000 dimensional integral. That's the reason. Curse of dimensionality. This is basically integration of exponential of x is high dimensional. If this is high dimensional, you are out of luck. Okay. In autoregressive model, remember they are normalized but very simple. So the pros is expressiveness, because this is not normalized. That means it is a very complex distribution you are looking at, because it's a function of a neural network directly. You assume the conditional. In that case, you can make it complex, but there is a limitation of how complex you can make it, because you can only make it as complex as you can find the normalizing constant. You cannot go beyond and make it such a complex, the complexity to such a degree that you are not able to find the normalizing constant. Then you are trapped. Basically, if you think of it like this, in all the models we've discussed till now, let's talk about autoregressive. There in VAE also that is true. We were using neural network to approximate the parameters of the distribution. Correct? In this case, we are using neural network to approximate the distribution itself. That's the main difference. And that gives us the expressiveness. So your mean and covariance are expressive. Does not mean your distribution is expressive. In this case, your distribution itself is a neural network, exponential of neural network, so neural network. That's why it is expressive. Of okay, so there are some two examples I'll give. One is Ising model is one where you can denoise. So the advantage, there is one more advantage I did not say. This likelihood is exactly, you can compute the likelihood exactly. Not exactly, but I mean, if you to the extent accuracy of z, you compute the likelihood. So it is used for denoising, and it is used for anomaly detection. These are two examples. But in general, it is very important because this is the basis of denoising diffusion model, which are scalable. So when I go to denoising diffusion model, and from there we'll go to flow matching, so those models are scalable, and the foundation of that is here. So without doing this, you cannot go there. So that is much more important historically, right? Hmm. Yes and no, both. Obviously, learning the distribution means learning the parameter. But here, learning the parameter means learning the weights and biases. So weights and biases are directly your parameter. In autoregressive model, it learns the parameters of the distribution. So weights and biases are used. The neural network output is what? Weights and biases. In this case, neural network output is what? Directly the distribution, exponential of that, log probability. So what you are using it for is the question, right? Even in other things also. In most of the things we have discussed, you will realize that we are using this neural network to approximate the parameters of the distribution. Not in GAN, but GAN was doing something else, but in most cases, right? Basically we are doing either of two things till now, if you forget about this. First thing we have done is we have used the neural network to approximate or learn the parameters of the distribution. Point or example here is autoregressive and VIE. Or we have used neural network to transform the sample of one distribution to sample of other distribution. Flow based GAN. But here we are using neural network to approximate the distribution itself, not the parameters of the distribution. That's the difference. At the end of the day, in all of this, you will learn theta only. That does not change. But ultimately, f of theta is representing what that changes. You had some question?
So you are saying that this one is used for denoising and anomaly detection. All the others also can be used for
Not exactly. Not exactly, because you are forgetting that there are some models where the likelihood cannot be evaluated, like GAN.
Yeah, if we can bear.
You cannot use, right? How will you evaluate the likelihood in GAN? The whole idea is you don't need likelihood, right? You can still use it for denoising, but you will don't get the explicit likelihood. Here you get it. When I say it is used, I mean it is favored because you get an explicit likelihood. Does not mean that others cannot be used. You can use it much easily once the model is trained again.
This like expressivity comes from the in exponential distribution. The density parametrics of the parameters of the network. The distribution need not to be analytical.
It is not analytical.
Like,
Exactly.
so like the expressivity comes from.
Yes, comes from the term that is inside the exponential, right? It's a very complex composition of function, what is sitting inside the exponential. Okay. So these are the cons and pros. So I have what? 3-4 minutes. I want to show you two examples. One is a denoising one. Let me write it down. The other one is a product of experts. That's another very interesting one. That I can show today or next day. That's fine. But the Ising model, let us see. So as I was saying, right, one of the main challenges of this thing is that this z of theta that is sitting there, right? And remember that z of theta you might also need to evaluate. I mean, you definitely need to evaluate. You definitely have to evaluate z of theta during training. There is no other option. But evaluating it during inference is also expensive because you have to solve that multivariate integral. Yes, once theta is known, you have to evaluate it only once. But you do need to evaluate it that once is also expensive. You don't need to evaluate it again and again, but it's intractable even when you have to do it once. So any example, any problem statement where z gets cancelled out is an ideal test bed for these models. Any test, any example where the z will get cancelled out somehow, the z will not exist during inference, is an ideal test bed for this. Now, when will it happen? It will only happen when you are comparing two things. So there is this example, right? So suppose I have a packet of sweets and I distribute it among the all of you, right? I have multiple packets, let's say, okay, one packet will not be enough. Multiple packets of sweets and I distribute it. Now, if someone gets 5 sweets, others will have to get less number of sweets because the total number of sweets I have is constant. Let's say I have 100 sweets. There are 30 students. So not everyone will get equal, but if someone gets 10, someone will get 1 because the total has to be 100, right? So if I tell only that you have got 10 sweets, you do not know whether you have whether 10 is a higher number or lower number. You don't know until and unless I tell you the total is 100. Because if it is 100, then you know 10 by 100 is 0.1. So there are 30 students, I am getting 10%, so I am on the higher side. So when you look at one sample, that's the problem. You need Z. Z is 100 here, right? But if I say that you got 10 sweets, I got 5 sweets, then you don't need the number 100. You know that he got more sweets than me without even knowing that 100 sweets was there. So whenever you will compare frequency or probability or likelihood of two samples, then it's fine to only evaluate the numerator. The denominator will not be needed. it will anyways get cancelled out. You can see if it is proportional, so it will just get cancelled out because it's not function of x. So in those cases, this will be very useful. And anomaly detection is one such case. That compared to the other samples, what is the probability this sample, what is the PDF frequency this sample is giving? So compared to the training samples, what is the frequency this sample is giving? That's what you need. That means you don't need Z for that. So that's why anomaly detection is a good example. So examples of energy based model. Example is probably a wrong terminology, application is better. So I think you write application. Okay. First one is, it is good for comparing likelihood of two samples. Okay. Because in that case, the frequency is enough and you can say which one is more likely, which one is less likely. Z will get cancelled out, right? This is useful in anomaly detection and denoising. Because in denoising, you are trying to find which pixel is having how much noise compared to the other pixels. So it becomes a comparison like that. Anyway, any case, data is coming. Is there a fault or not? If there is a fault, the distribution of the healthy data should be different from the distribution of the faulty data. It can be electrical circuit, it can be structural health monitoring, it can be all of those, right? Is there an anomaly or not? Now that anomaly, what is the reason, you don't know. Whether it is a wrong sensor measurement or actually there is a fault, you don't know that. But it's an anomaly. The anomaly can also be because of environmental factors. So denoising, I will give you one example. So one of the earliest energy based model is the Ising model. I think those who have done machine learning course might have studied it, might not have studied it, because many machine learning course nowadays do not cover this. But this is one of the basic models, one of the initial models that were proposed. Anyone knows what is Ising model? What is it? Close. Anyone else knows Ising model? APL 405 did not cover? It generally does not cover actually. So Ising model is basically about denoising. So the idea is that you or we have an image y, which will, and the image will take either 0 or 1. That's what he was saying, that magnetic changing the pole. And let's take a small one, so 3 cross 3. Okay. And this is a clean image. This is not known to us. And measurement, and this is what we have measured, x 0, 1, and this is what we have. Okay. So the idea of here is that given x, can you estimate y? So what you want to find out, that given x, you want to have an estimate of y. The idea is x is noisy, so some 1s has become 0, some 0s have become 1. So given x, where some 1 has become 0, 0 has become 1, can you find y and correct those values? So it's like a denoising model, but as a very discrete kind of denoising model. So to do this, one of the most popular one is that is used is the thing that is used is something like summation over I psi I xi yi plus summation over I comma j belonging to E psi I j yi yj, and I forgot to write what will be outside. Any idea what will be here? Exponential. That's what we have been doing. And before that 1 by z. So 1 by z exponential of summation over I psi I xi comma yi plus summation of I comma j belonging to E yi comma yj. Now I need to define this thing. What is psi I and psi ij? These are like potentials. Okay. What is psi I xi comma yi is saying? It is basically tracking that xi and yi has some correlation. At same pixel location, what you are measuring and what is the actual value has some correlation. That's what it is tracking. So this is correlation between x and y at I. And what is this? This is saying that whatever is the neighborhood, this would have correlation. If my neighborhood is 1, the chances of me this pixel location being 1 is higher. That correlation this is tracking. So this is the neighborhood correlation.
Sir, it would be
Yj, yeah, it's j. Oh, it did not come. I was saying j only. Okay, and belonging to E, what does it mean? Whatever is neighborhood, they are connected by edges. So this is the edge set. So if I and j, whenever they are connected by their neighborhood, they are connected by edges. If they belongs to that edge set, then only you calculate it. If they are far apart, they are uncorrelated, so you don't need to calculate. So only the neighborhood you will calculate. Otherwise, it will be very expensive. That's why. Repeat. You decide. I mean, in this case, it is 3 cross 3, right? You can always consider whatever is the nearest point is connected. So think of a 3 cross 3 grid. Yeah, in this case, it is the 2D, 3 cross 3 grid, right? So the first point is connected to 2 points. The second one is connected to 3 points. The middle one will be connected to 4 points. So in that sense, right? So something like this is how it looks, right? 1, 2, 3, 4, 5, 6. And now you can see the edges, right? These are the edges. And then from here you can have, I mean, let's say these are y, and then you can have x, and x1, x2, x3, x4, x5, x6, x7, x8, x9, or x1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1. In that sense, okay? And this gives you the connection. Okay. So this is the Ising model. What you can do is, how can you solve that problem? You will basically maximize probability of y given x. Given that you know this model, let's assume you know this model size and known to you. What you will do is you will find out the y that maximizes y given x. So given x, what is the value of y that is the probability of which is maximum. So basically, you find y star is equal to argmax probability of y given x, which is equal to argmax probability of y comma x, and you can only work with z is a constant, you can remove it and you can work with it. I'll change one thing here very quickly. This I should write as because f theta we write when there is a neural network. This Ising model does not have a neural network, so I. Okay, so you can just once you know if you know size, you just maximize it to find out y, and for that you don't need that z, that's a constant. So you this is a one example where you can use it. I'll stop here. The other I've already passed the time. The other example I wanted to discuss is actually very interesting, which is a product of experts. But we'll discuss that next time. Then we'll go to RBM, and there the actual derivation and mathematics and training will start. Okay. Today was more about a high level introduction to energy based model. Okay. Okay, so we'll meet on Friday. Thank you.